Hello friends, I am Saurabh Gupta. I am a student of IIT Bombay and currently I am studying mechanical engineering. I have written my JEE in the year 2010 and I secured an AR of 443. And I have cleared the second stage of chemistry Olympiad conducted by HBCSE. Today we are going to discuss something about alkenes and alkynes. Now these are again another class of functional groups in organic compounds which have got some special properties, especially alkenes. And alkynes, the properties are quite similar to alkenes, but the differences we will study in detail. And this is the continuation of the alkenes, alkynes, alkyl halides, alcohols and ethers. These are all the functional groups which decide the properties of an organic compound, and hence we need to study the reactions, the physical properties, the chemical properties, the preparation of these compounds in detail. So in this chapter what we will be studying will be the reason why the alkenes and alkynes are different from alkanes, that is the structural differences between them, and that will decide what are the differences between the properties, and that will lead to the chemical properties, and that again will tell us how can we prepare these compounds. So everything is interlinked to each other and everything starts from the structure. So first we will be discussing the structure, then some preparation methods of alkenes. The first we will be studying alkenes and then we will be studying alkynes. So first the structure of alkenes, preparation methods of alkenes, chemical reactions of alkenes, and then we will go to alkynes. So let us start the lecture. Let us see first alkenes. Alkenes, as we know, they are the organic compounds which contain this type of groups: R, R dash, R1 dash, R2 dash, etc. etc. So these four can be any groups and you can have so many number of alkenes possible. So now what is the structural difference between the alkenes and alkanes? What difference comes in the properties of alkenes and alkanes due to this structure? First of all thing, the difference between the structure is that there is a pi bond present over here. So this is an sp2 carbon as we know, and so there are 3 sigma bonds and there is one pi bond which is something like this. So now this pi bond characterizes all the properties observed of alkenes. That is, in chemical properties we will see the electrophilic addition over alkenes, and in preparation we will see a type of reactions called the elimination reactions which we will study in detail. So this will be the start of our organic chemistry reactions, where we will study two important reactions. One is the elimination reactions and another is the electrophilic addition reactions. Fine. So now because of this pi bond density, what changes come in the physical properties? Physical properties improve. Why? Because this pi bond creates a kind of dipole moment, because this is an sp2 carbon and these carbons might be sp3 or sp or even sp2. So there is a kind of dipole moment over here. So they are slightly more polar than the alkanes, but still that polarity is not enough to distinguish the physical properties of alkanes and alkenes. They have quite the same physical properties. All of them are insoluble in water and quite soluble in the non-polar compounds like benzene, chloroform and carbon tetrachloride, and the density of these compounds are less than that of water. So the physical properties are quite the same, but the chemical properties, there is a huge difference between the chemical properties of alkanes and chemical properties of alkenes. The pi bond, because of this pi bond density, these alkenes are very much reactive as compared to alkanes, and they undergo a reaction called electrophilic addition reactions, in which this pi bond density, as we know, this pi bond is not as strong as sigma bond. So this pi bond can be broken with little bit amount of energy, and that much energy can be regained by the formation of some other bonds. So that is why these alkenes undergo chemical reactions which we will be going to study. But first of all thing, we will be studying the preparation of alkenes. So in the preparation of alkenes, we have some reactions. First of all thing, alkenes can be prepared from alkyl halides. Dehydrohalogenation dehydrohalogenation of alkyl halides. Sorry, hydrogen halides, not halides. Dehydrogenation, okay, alkyl halides only. Second, we can prepare this from the alkynes. Alkynes, we know that they are having a triple bond, and that means if we remove one bond, one pi bond, or we dehydrogenate it, that is, we put some hydrogen in it, we can get a alkene. So, hydrogenation of alkynes. Now this is quite simple. You just take an alkyne, you add a hydrogen, and you get one alkene. So third one will be acidic dehydration of alcohols. Then fourth one will be from, okay, these three are the major methods of the preparation, and other methods we will see after discussing in detail all these three methods. There is a lot to discuss about these three methods, and then we will go for some other preparation methods of alkenes. First, we will be considering the hydrogenation of alkynes. Now, hydrogenation of alkynes is a very simple process, but suppose we want to get specifically cis alkenes or trans alkenes. Alkenes, we know they are having a double bond, that means they are having restricted rotation, and that means they can show geometrical isomerism. And we have discussed a lot about it, and now we will see how can you get from alkynes. Suppose this is one alkyne. From here, if you do some hydrogenation, how can you get particularly a cis alkene, or a trans alkene, or a cis alkene? Now, this trans alkene can be obtained by reacting this with sodium in liquid ammonia. Now, ammonia, as we know, in room temperature it is a liquid, and if you put some sodium in it, sodium powder is available in the lab, and if you react with the alkynes, then you get a trans alkene. The mechanism of this is slightly complicated because this involves some anion radical intermediates. We have studied only three kinds of intermediates: carbocation, carbanion, and free radical. Now, this is a combination of carbanion and radical intermediates. We will not be discussing the mechanism of this because it is out of scope of this lecture. Now, what about cis alkenes? What about cis alkenes? What I have drawn here, trans alkenes. Now, cis alkenes we can get, the same process does not give us cis alkenes. We have to apply a completely different process, and that is a very complicated name, that is Poisson palladium charcoal. So, we are going to use palladium and charcoal, but the point is it should be Poisson. Poisson with what? Poisson with some sulfur compounds and lean. Now, these two are compounds which poison this palladiated charcoal. But what is the meaning of exactly poison? The meaning of poison is they are slightly deactivating groups. That is, they will deactivate the reactivity or the catalytic property of palladium. So, if you just want to write a reaction, it can be a specific one. Then you can write, suppose this is CH3 and this is H. Then if you treat it with Na and liquid ammonia, you get a trans alkene with CH3 like this and hydrogen here. Now, if you treat it with this palladiated charcoal, but a poisoned one, which is also called the Lindlar's catalyst. Remember, this is a very, very important catalyst and will be asked in very frequently in questions. We have CH3 and hydrogen. So, this is a cis alkene and that is a trans alkene. So this was a very simple preparation of alkenes from the Lindelof catalyst and sodium and liquid ammonia. Now let us go towards the second process. The second is the preparation of alkenes through the dehydrohalogenation of alkyl halides. But before that, we need to see some very small property of alkenes which is required for the study of the dehydrohalogenation. And the dehydrohalogenation is exactly what is called the elimination reaction. We will be studying the elimination reactions of alkyl halide to produce alkenes. So what we need to study before that is some stability of alkenes. Now this stability of alkenes will decide which alkene will be produced by the elimination of the alkyl halide. Suppose we want to produce a specific alkene, whether what steps should we follow so that we can get it from a particular alkyl halide. For that we need to know something about the stability of alkenes. Now this stability of alkenes can be measured via thermodynamic data quantitatively, that is how much stable one cis alkene is more than the trans alkene, or how much stable one trans alkene is more than cis alkene, and that is done by heat of hydrogenation. We know that alkenes contain double bonds, and double bonds can be hydrogenated to give alkanes. So C double bond C, R dash, some H and R. Now this, if you treat it with hydrogen, if you hydrogenate it, you get an alkane. So this will release some amount of heat, delta H naught, and if you take 3 alkenes, let me take some particular examples. I will take 1 butene, I will take 2 butene, but here I will take the cis ones, H2, we get the same alkane, R dash and R are CH3, 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 here also CH3, CH3, delta H naught, and I take trans alkene. Now all the 3 alkenes have got same molecular formula. We know they are isomers of each other and they give the same alkane on the hydrogenation. So what do you expect the delta H naught values, whether they are same or whether they are different? In reality they are different. Why? That is because of stability of the difference in the stability of these 3 compounds. It is observed that the delta H naught value for this is minus 30.3 kilocalories per mole. For the cis alkene it is minus 28.6, same thing, kilocalories per mole, and for this is minus 27.6, that is for the trans one. So that means the lesser is the heat of hydrogenation, that means more the stable the alkene is. What is the heat of hydrogenation? If you take a potential energy diagram, that is, if suppose this is these are the 3 different alkenes. We know alkenes are slightly more stable than alkanes, so here is the alkane, and we have the same alkane, so that means the potential energy is only 1. But we have 3 different alkenes. Okay, they are not different alkenes, they are different isomers, but still, as we have seen that there is some stability difference, that means there is some difference in the potential energy of the 3 alkenes. So we draw 3 lines this way. Now see, this alkene is having the minimum distance, that means it is the most stable alkene, that is, so this must be the trans one, this must be the cis one, and this must be the 1 butene, and this must be cis. So you see that heat of hydrogenation, the lesser it is, the more stable the alkene will be. So that means trans alkene is the most stable and compared to cis alkene, and the cis alkene is even more stable as compared to the 1 butene. So what is the general order? How can we determine, without experimenting and calculating the values, how can we say what is the order of stability of alkenes? Now doing a lot of experiments, it is observed that the most substituted alkene is the most stable one, and if the alkene is same substituted, then the cis alkene is less stable than the trans alkene. The reason why cis alkene is less stable than the trans alkene can be seen by here. Here we see that the CH3 groups are having close to each other and having good amount of repulsion. That means that decreases the stability of the compound. But here it is quite favorable that two CH3 groups are far away from each other and they do not have that much of strain. So this was an important concept regarding the stability of alkenes, and this concept we are going to use in deciding what will be the product of an elimination reaction. So let us now move on to the dehydrohalogenation. Dehydrohalogenation of alkyl halides or it is called 1,2 elimination or it is called beta elimination. Now all these three names will be clear when I write down one simple reaction over here. Suppose consider this chloride, that is a hydrogen, and there are some groups. Now when this is treated with KOH, C2H5OH and heat, gives you an alkene of this sort. So you see that dehydrohalogenation, one hydrogen, one halogen. So in this case it is dehydrochlorination. So one hydrogen and one halogen are removed and you get an alkene. 1,2 elimination. Here exactly what happens is, from this overall molecule, if you minus HCl, what do you get? Alkene. That is if you consider the molecular formula for this and the molecular formula for this. There is a difference of HCl molecule. That means it is elimination. And what type of elimination? Suppose this is the first carbon, then the elimination is between the first carbon and the second carbon. That is, if the halogen is present on the first carbon, then the hydrogen will be taken from the second carbon, and this is a very, very important condition for this elimination to take place. Otherwise this elimination cannot take place and this reaction will follow some other path and give you some other product. This is not the only product which is possible with this set of reactants, with this set of reagents. There are many other products possible, but by controlling the reaction conditions we can ensure that we get this as our major product. We will be discussing that further, but let me tell you, if you don't have a hydrogen in the 2 position, then you won't get an alkene. This 2 position can be over here also or can be over here also. Suppose you have a hydrogen there, fine, you will get an alkene which is something like this, no problem. But anywhere adjacent to this carbon there must be a carbon which contains a hydrogen. Now why is it called a beta elimination? Very simple, the same reason. Scientists call this as alpha carbon which contains the halogen and the next carbon as the beta carbon. So that means it is the elimination from the beta carbon, that is this hydrogen is gone from the beta position. So this is a very simple reaction in which from alkyl halide you get a alkene. But now this is a very, very important reaction to study. If we study the mechanism, we learn a lot of principles in organic chemistry which are helpful in the further study. So let us start with the mechanism of this reaction. We have to see the mechanism of this reaction and determine whether we can get a particular alkene from a particular alkyl halide, because all alkyl halides cannot produce. Suppose you want to get this particular alkene, CH3, C2H5 and hydrogen. Suppose you want to get this particular alkene, then which alkyl halide should you choose such that you get this as your major product? That is very, very important, because if you choose some halide that might not give you the major product as this one, that might give you some other product under the reaction conditions. So we have to control the reaction conditions, and we have to choose a particular alkyl halide properly so that we get this in good amount. That is why it is very important to study the mechanism. There is no other reason. Just to produce this in major amount, because that is what is industrially useful. You need to get a compound in good yield, and for that we need some preparation methods, and we choose the best and the economical preparation method, and this is a very good preparation method, at least in the laboratory level. So now let us go for the mechanism, but before the mechanism again we require the knowledge of three important terms. One is what is electrophile, second is what is nucleophile, third is what is a transition state, and what is a transition state, let it be the next one. What is a leaving group? Transition state or intermediates. Intermediates we have already seen. What are intermediates? They are produced in the middle of the reaction, that is in between the reactants and the products. But what is transition state? That we will be studying further. Now first, what is an electrophile? Now electrophile is a compound which is electron seeking, that is it is deficient in electrons. For example, BF3. We know that boron has got an empty p orbital, although not fully empty because the F is having back bonding, p pi bonding, but still the boron orbital is empty and it acts as an electrophile. That is, if suppose any pi bond density is available, if these are the orbitals, now this pi bond density can actually be donated into this empty orbitals and taken away from this. So the pi bond breaks and a new bond between the carbon and the boron forms. So that is actually what is an electrophile. Other examples of electrophile. Can you tell me whether this is an electrophile? No, this is not an electrophile. Although there are only 6 bonds, but there is a lone pair of electron and there is no empty orbital. So hence this cannot accept any electrons from anywhere, so this is not an electrophile. Now what about this? CCl2 with a lone pair of electrons. Is this an electrophile? No, this also is not this is actually electrophile, although I am showing a lone pair of electrons over here. When you draw the Lewis structure, you will see that this is sp2 hybridized and there is an empty p orbital. This type of intermediates are called carbenes. This is not necessarily always an intermediate, this is a very important reagent also, and we will be studying the reaction with this reagent with alkenes when we go for the chemical properties of alkenes. Now, what is a nucleophile? Nucleophile is a substance which can donate electrons to someone, a donate electron pair to someone, just like a base but very much different from a base. Basicity and nucleophilicity are two very much different concepts. Nucleophilicity is based on the kinetics of the reaction and basicity is based on the pKa value. What that means is, first let us see what is nucleophilicity. Nucleophilicity, for example, Cn minus. Here the C, suppose a carbocation is there. We have seen what is a carbocation earlier. Suppose there is a carbocation. Now this is an electrophile because this has got an empty p orbital and electron density from carbon or nitrogen can be donated into the p orbital. That means here the Cn minus acts as a nucleophile. It is a nucleus seeking center. It needs a nucleus or a positive center to donate its electrons to. So that is a nucleophile. But we also know that Cn minus is a base. But so what is the difference between nucleophilicity and basicity? As I just now told you, that basicity is based on, suppose HCl, H plus and Cl minus. Basicity is the concept of this equilibrium. How much of the equilibrium is shifted in this direction and how much is shifted in this direction. For example, if you take these two, then we know that HI is a stronger acid than HCl. That means this is much more shifted towards in this direction. That is, much more H plus is produced as compared to HCl. So that means that this is more basic than HCl. And as you will see that I minus is also more nucleophilic than Cl minus. Why is that? That is because if suppose there is a carbocation like this, suppose there is some electrophile present over here, electrophile is represented by the letter E, then how much fast this I minus can or this Cl minus can donate its electron density into the electrophile, and I minus donates electron density very quickly and the rate of reaction is very, very high. And that is exactly the difference between the concepts of nucleophilicity and the concept of basicity. Basicity, you can see, it is an equilibrium concept. That is, it depends on the position of the equilibrium. How much the equilibrium shifted this side and how much is the equilibrium is shifted this side. While nucleophilicity, based on the kinetics of the reaction, how fast the reaction can happen. That is, if the nucleophile can make the reaction faster, then it is a stronger nucleophile. An example and the difference between will be very clear with this example: H2O and HCN. Now HCN is a stronger acid than H2O. What do you say about the nucleophilicity? OH minus, CN minus. OH minus is more basic than CN minus because HCN is a stronger acid. But what about the nucleophilicity? Cn minus is greater than OH plus. So nucleophilicity and basicity can have simply opposite orders, but they can have same order also if you consider something like OR minus greater than OH minus, much greater than RCO2 minus. This is a carboxylate ion, hydroxide and alkoxide ions. So this is much more nucleophilic than this. This is more nucleophilic than the OH minus, and OH minus is much more nucleophilic than the RCO minus. And we also know that this is the order of the basicity. This is more basic than this, and this is much more basic than that. So nucleophilicity and basicity can have the same order, or they can have the reverse order, as in this case. So this was the concept of electrophile and nucleophile. And the alkenes is an electrophilic addition reaction. Alkene is a kind of nucleophile. It has got a pi bond density and it can donate it to an electrophile which comes near it. Suppose this is an alkene and this is electrophile, then this pi bond density can be donated to the electrophile, and that what causes the properties, the chemical properties of alkenes, the addition reactions. There we will have an electrophile and the pi bond density will be gone and new bonds will be formed in this system. So now leaving group. Now in the reaction of elimination, you observe one thing, that you have an X, you have an H. Now this X has to leave this system along with this H, but this H won't leave just like that. This will be abstracted by a base, and with the base it will be the obviously KOH and C2H5OH, as I have mentioned in the reagents. Now this X is actually the leaving group, or halogens has to leave the system, and the better the leaving group is, the better will be the more faster the reaction will occur. And that means it is a property which is related to basicity. The lesser basic it will be, the lesser basic the leaving group it is, the lesser basic the group is, the better are the leaving group properties. For example, OH minus and I minus, we know OH minus is much more stronger base as compared to I minus, and hence the leaving group capabilities are just the opposite. I minus can leave the system as it is, that is Ci. This bond can be broken very easily as compared to COH bond. This bond will be requiring much more energy as compared to this one because of this basicity order. So that is the leaving group. What is this transition state and intermediates? For that, let us directly go to the mechanism of the reaction. That is, we are going to see the mechanism of the elimination reactions. Now there are two ways in which the reaction can take place. One is a unimolecular reaction and the other is a bimolecular reaction. What is the meaning of that? That is, in the slowest step of the reaction or in the rate determining step of the reaction. We have seen in alkanes also there is something called a rate determining step, and which is the slowest step. I told you if A is giving B, B is giving C. Now the formation of C completely depends on the slowest step among these. Suppose A gives B with a speed of 100, but B gives C with a speed of only 10. So what do you think is the overall output? The overall output is we are getting only 10. Although 100 objects are ready over here to be reacted with some reagents, but we are getting only 10 because B to C the reaction is very slow, and hence that will be the rate determining step. That will determine what exactly, how much fast the reaction can proceed under the given conditions. So in the rate determining step, the two pathways of the elimination reactions differ. In one of the elimination reactions, there is only one molecule which decides the rate, and in the other one, we have two molecules which decide the rate. So we have E1, which is the unimolecular elimination reaction, and we have E2, which is the bimolecular elimination reaction. The difference between these two reactions is that in E1, in the slowest step or in the rate determining step, the rate of this reaction is determined by the concentration of only one species. But in case of E2, the rate is determined by the product of the concentration of species 1 and species 2. This will be more clear when we study the mechanisms in detail. So let us start with E1 mechanism. Now E1 mechanism is a two-step reaction, and out of the two steps, one is the rate determining step or the slowest step. So suppose we have one halide which looks like this, or we can just remove this carbon for a while. We have X and we have H. Fine, and this has got two hydrogens, that is no need to mention. We have KOH, C2H5OH, and heat. Now exactly what is this reagent? This reagent is nothing but C2H5O-. These two react in such a way in order to produce K plus and C2H5O- and H2O. K plus C2H5O- and H2O. Now this is the species which is going to react with this molecule. But before that, there is one small step in this reaction, that is the first step and the rate determining step. What happens is this X leaves the system. As it is a very good leaving group, the leaving group properties will determine how fast the step it is, and there are other factors which determine how fast this step would be. That is, if this X leaves, what do we get? What we get is this bond breaks. That means this carbon gets a positive charge. And now what happens? What happens is that we get a carbocation. C, CH, and carbocation H plus, and there is production of X minus. So this is the first step in the mechanism. This is what happens in E1 mechanism. Then what does this entity do? This entity comes in the second step of the reaction. Now in the second step, what happens is, this is a base, we know. This is actually a good nucleophile also, but here we need to act this as a base, and we can change the reaction conditions such that this acts as a base and not as a nucleophile. So First it acts as a base, and you see this hydrogen. What is the special property of this hydrogen? The special property is that if the base abstracts this hydrogen, then a double bond can be formed over here. How? Just check this out. C H C, a positively charged species is present. If we have this B minus or the base, this takes up this hydrogen or donates its electron density into the anti-bonding orbitals of the CH bond, and this CH bond exactly cleaves in this manner. That is, the bonding electron density goes back to the carbon, and now carbon has got some electron density, so it will be donating it into the MTP orbitals of the carbocation, and hence forming C C double bond CH2, hence forming this alkene. So you see that there are two steps in which in the first step we get a carbocation, in the next step we get the hydrogen is abstracted by the base and we get the alkene. But now, why is this step the slowest step? We can show that by the help of an energy diagram. And here comes, and what are the reasons and how can we make this reaction faster? What are the factors that we can apply so that this reaction is proceeding faster? Because we value the time as well as the money. So if this is an economical method, this must also be a fast method. Otherwise it is a useless method. Now, the energy diagram for this overall reaction something looks like first peak, second peak, and then there is this. Now what is exactly this energy diagram? Now here you can say this is the reaction coordinate. Now the reaction coordinate are the species that are forming continuously in the reaction, and this is the potential energy which is increasing in this. Now our initial product, which is the halide, is over here. Now it goes to a peak and it comes down, and here what we get is the carbocation. This is the carbocation, and here what we get is the alkene. Now what is this energy diagram? That is the energy diagram like if we want this to convert into this, that is we want the entities over here to go over here, then they have to cross a barrier or they have to jump over this barrier in order to come there. Imagine this like a hill. So it has to climb this entity and it has to reach the maximum, it needs some energy, and here what we have is a transition state, because here this reactant is converting into this intermediate. So we have a transition state for that, and the transition state looks like this. That is, we have this bond cleaving and a partial positive charge developing and a negative charge developing over here. Now the stability of this transition state is very important because that determines the rate of the reaction. The more stable the transition state would be, the lesser would be the energy barrier. So suppose this carbocation, we can make it more stable. That is, we can make this transition state more stable by some manner such that the energy barrier reduces and we get the reaction faster, because then lesser number of molecules, then the molecules will have to cross over a limited barrier or a small barrier, and more number of molecules can cross over and we can have a good reaction speed. So what we can do is, if we can rearrange this transition state, or we rearrange the carbocation, that is, we shift the methyl group from here to here such that the carbocation comes over here. I have shifted the methyl group from this carbon to this carbon. Let me show that in blue. I have shifted the methyl group from carbon 1 to carbon 2. So now what do you get? You get a 2 degree, or actually 2 degree carbocation, because this carbon is connected to this carbon as well as connected to this carbon. Earlier what we had was a primary carbocation, that is, it was connected to only one carbon. But now you see that we have got a secondary carbocation and hence it is more stable. That means our reaction intermediate is more stable, and the transition state which leads to this intermediate is this. The transition state is something like CH3. We have delta positive charge over here and a delta positive charge over here. We have a delta negative charge over here. Now, this is how the transition state looks like. Positive negative cancel, positive negative cancel. Now, this transition state is slightly more stable as compared to the original transition state, because here this charge has got more number of hyperconjugating structures. So now the reaction has got a lower pathway and hence it will proceed through this way. And if we go for that reaction or that pathway, that the carbocation is forming over this carbon, and if you write the product, how it looks like? It looks like something like this. I will write CH2, hydrogen is present over this, there is a carbocation over here, and we have a CH3 over here. Now the base has to abstract a hydrogen from here so that we can stabilize the negative charge and form an alkene. Now there are so many alpha hydrogens possible. As I told you, not only it is not necessary that this hydrogen is always eliminated, just because initially this was in the beta position as with respect to the halide. We just require a beta hydrogen to the carbocation. If the carbocation was here, then this was a beta hydrogen which was available and we could use it. But now we have multiple choices. Let me explain. We have one hydrogen like this, one hydrogen like this, and we have 3 hydrogens over here. So now totally we have got 5 beta hydrogens which can be abstracted by the base and can give some alkene over there. But which of these 5 hydrogens will be abstracted by the base? As you can see that the set of these 3 hydrogens are going to give you the same alkene, that is this alkene. Let me draw the structures of the 2 alkenes also. C double bond C, and we will have CH3 like this. So this will be giving you 1 propene. What about this alkene? This alkene, I think I have misplaced a carbon somewhere. Yes, we have 1 butene, because there are totally 4 carbons. Now, this positive charge, if this hydrogen is abstracted, then we can form alkene in between. That is C double bond C, CH3, CH3. So that means these 2 set of hydrogens will give you a trans alkene, a 2 butene, and the set of these 3 hydrogens will give you 1 butene. So which of the 2 products will be formed? Both will be formed. Why? Because in organic chemistry all possible products are formed, but in various proportions. So which proportion will be more? That we can answer through the transition state. That is, if the energy of the transition state is lower, that product will be more in number as compared to the other one. Now consider the transition state for the 2-butene. For that, the transition state will be something like this: delta positive charge, hydrogen going away, having delta negative charge. So if you see this has got 2 substituents, from 1 carbon over here, another carbon over here. This has got a double bond character and it is a very stable double bond, because we know this substituted alkene is more stable than that. So that means the transition state for this is more stable as compared to this, and hence this will be the major product. This is called the Sedgwick rule. Sedgwick rule. Now this Sedgwick rule is used to find out whether what is the major product out of the possible isomeric products, because we know that elimination can give two different products, although they will be isomers of each other, but which would be in major amount, which would be in the minor amount. So this rule can be used to calculate that, and we have seen why that major product is favored because of the lesser energy of this transition state. So there are two transition states in this. One determines whether the rearrangement will take place or not, that is whether we will get the unrearranged halide or alkene, or we will get the rearranged ones. So that means suppose we want to get this one, we cannot get it from this, because although halide is present over here, the carbocation shifts over here, or it rearranges to get a stable carbocation. So that means if you want to get this type of alkene, we need to apply, or we need to take some other halide and not this halide. And actually that can be obtained by using a bulkier base as compared to this C2H5O minus. Suppose if we take kind of base which is something like this, which is called a tertiary butoxide. We take K plus over here, then this is called tertiary butoxide minus K plus. So if you take that base, then this kind of product is possible, and that is called the Hofmann rule. Hofmann rule. That is, if you take a bulkier base, then the least substituted alkene will be produced, because if you look in this transition state, in this transition state, the base comes into the picture, and if you take, suppose this is our carbocation. Now if we'll take this itself, this is our carbocation. Now the base approaches this molecule, and the base is a very bulky one, and the base is actually increasing in size when you put it in water. Why? Because solvation of that thing. If you solvate it, then the size of this base even becomes larger. So then it is easier for that to approach these hydrogens as compared to this hydrogen, because these hydrogens are more open, and these are not so open. And in fact, if you take a more bulkier or more substituted alkene, for example, if you take something like CC, one carbon here, one hydrogen, one carbon here, the same alkene, I am just adding this group, methyl group, and this kind of thing. Now here what happens, suppose I have this carbon instead of this hydrogen. Fine. Now what happens, this has got two hydrogens, that is, if the carbocation comes over here, now tell me whether the carbocation will shift or not. Here also it is a secondary carbocation, and here also it is a secondary carbocation. That is, if you shift this carbocation, what we get, C plus, this methyl group shifts over here, we get C, C and hydrogen, and we have three hydrogens over here. Now again there are two beta hydrogens, that is, for the base to abstract, three hydrogens over here and one hydrogen over here. But now what happens is, this hydrogen is attached to a tertiary carbon, which is so much overcrowded because of these bulky CH3 groups. So that if you take a bulkier base, for example tertiary butoxide, then in that case these hydrogens will be abstracted instead of these. So we get a lesser substituted alkene because of this hydrogen was abstracted. The alkene would have been C and C, and now if this hydrogen is abstracted, we get CC and CCC like this. So you can easily see that this alkene is lesser stable than this alkene, but still this is a major product in this case when we use a bulkier base. That is called the Hofmann rule, and that is due to the instability of the transition state, the second transition state. So you see that the course of the reaction is completely determined through this energy diagram. That is, if you know the transition states, you know the intermediates, and you know all possible transition states, then you can determine what factors affect the rates of this reaction and what can change the course of the reaction. That is, if you want to produce this alkene, then what reagent to use. If you want to produce this type of alkene, then what reagent to use. And you can apply similar conditions on the alkyl halide also. That is, we can choose a proper alkyl halide so that we get a proper alkene. We will be seeing some of these type of questions in advanced level so that you get a much more better idea. Now, this is one possible elimination reaction, a method of elimination reaction. The other method is the E2 reaction, which is the bimolecular reaction. And tell me, why is it this called a unimolecular reaction? As I told you, the rate of the reaction. Now, this step, that is conversion of carbocation, is the RDS, or the rate determining step. And here there is only one entity present, that is only the carbocation. So the rate is nothing but the concentration of the carbocation. So if you increase the concentration of the base, in this case the rate of the reaction won't be increasing, it will be unaffected because it's a first order reaction on this entity. So, and that is how actually we find out whether it is a unimolecular or bimolecular, by increasing the concentration of the base. In case of E2 reaction, you will see that if you increase the concentration of the base, the rate of the reaction will increase, but in this case it remains unchanged. So let us see what is the possible mechanism, and let us try to understand it for the E2 reaction. Now, elimination bimolecular suggests that there must be two molecules present at the slowest step, and there are only two important molecules in this reaction. One is the alkyl halide itself and another one is the base. So this suggests that E2 elimination reaction is a one-step reaction. So it is a one-step E2 one-step reaction. That is, you have only something like this. You don't have two peaks, you don't have got two transition states. It is a single step reaction, and hence there will be only one transition state. So now, and there is no intermediate which is produced, directly reactant, product and the transition state. There are no intermediates in this case. The intermediate in the previous E1 reaction was a carbocation, and we saw the energy diagram looks something like this. So we see that there is an intermediate formation and there are two transition states. So right now we are not bothered about this, we have already studied in detail. Let us see E2 mechanism. Now the most important feature of the E2 mechanism is not that it is second order or not that it is bimolecular, but the stereochemistry of the reaction. That is the most important feature of the E2 reactions. But let me just give you a general idea about E2. Now in this case, what we have here is, this is initially our reactant and this is the reagent. Now these, as we know, in a single step they should produce a product. So what is the possible transition state? How does it look like? The transition state looks like clearly same as E1, but only the difference is in E1 we had production of negative charges and positive charges like this, and this was the only change that we had in E1, that is, this was a transition state. But now in case of E2, the whole process takes place together. That is, first the halide leaves, which creates a positive center, then this carbon tries to donate the electron density, which is supported by the abstraction of the hydrogen. So all the three processes happen simultaneously in a single step. So we have something like this and we have something like this. And so now if you calculate the negative charges, we will get overall a delta negative charge, which was the case earlier also. So this is our transition state in case of E2, which will appear over here. This is our transition state. So transition states look something like this. That is, there is a double bond formation and there is a breakage of bond between these two and a formation of bond between B and H. And as I told you that the double bond is quite lesser reactive as compared to a single bond. So this that favors the reaction to be going in the forward direction. Now, what is the product here? Product is simply C double bond C and whatever groups are attached to it. Suppose we have a CH3 group, we have another CH3 group, and we have hydrogen and we have hydrogen. We will get CH3, hydrogen, CH3 and hydrogen. But now the cis alkene or the trans alkene production is completely stereospecific. It is very much depending on the stereochemistry of the reaction. Let us see how. Let us look at this transition state. Having a closed loop, we observe that if this hydrogen and this alkyl group are present on the same side, that is, they are present something like, I will remove this diagram because of no use to us now. We have studied the importance of this. We take something like C, this hydrogen, this X, and we have a base over here. So now, if our transition state is something like this, then what is wrong? We can have a transition state which looks like this, that is a hydrogen which is anti to X, or a hydrogen which is very much close to X. What is wrong in this, and why is this the only transition state possible? That is because this transition state is more stable than this transition state, and the reason is the repulsion between the B minus and the leaving group X. The repulsion between these two causes this hydrogen and this X to be as far away from possible, and the maximum distance that they can achieve is 180 degrees, but they should be coplanar. If they are coplanar, that is in the same plane and they are anti to each other, that is they are at 180 degrees angle, then they are maximum far away possible from each other, and hence the base can abstract this hydrogen very easily as compared to this case, and this will be the very much stable transition state. So that is exactly the stereochemistry we want, that is the hydrogen must be anti to the chlorine, and if there is no hydrogen present anti to the chlorine, then this elimination cannot occur. Although if we have an hydrogen over here, this hydrogen should be anti to this hydrogen, otherwise this reaction cannot occur. If this cannot convert into a conformer or in some other configuration in which this hydrogen is not anti to X, then this elimination will not occur. And by conformers, that means there is a very good use of conformers in this, which we will see in the advanced level. I will give you a question in which you will see that. So for the elimination to happen, the molecule should go into a lesser stable conformer state, and hence the rate of the reaction will be very less. That is because the molecule is in the lesser stable conformer, and only in that conformer we have an anti-hydrogen and X. Now to give some details for that you understand better, consider this. We have a cyclohexane ring, we have Cl this way, or we can say we have a hydrogen this way and a Cl which is up, a tetrahedral shape. Now we have a hydrogen here and we have a CH3 group over here. Now this CH3 and this H are parallel and this H and Cl are parallel. Now can this thing happen, that is, can the elimination take place now? It is better if you draw it like this hydrogen and this Cl. We see that this hydrogen and this Cl are coplanar to each other and are anti to each other, and hence now the elimination can happen, that is the base can abstract this hydrogen and we can get a double bond over here. But suppose I put a CH3 group over here, then is it possible that you get this type of alkene, CH3 or this hydrogen? Now this is a very specific geometry, that is the hydrogen is in this way and the CH3 is anti to the chlorine. Now can we get this type of a alkene. If we want to convert this hydrogen halide or this cyclohexane ring into this alkene through E2 mechanism, that is, I will apply the conditions so that E2 mechanism elimination will take place, then tell me whether this alkene is possible. This alkene is actually not possible because this Cl and this hydrogens are not coplanar to each other or not present in the antiposition to each other. But we can have elimination from this hydrogen and this Cl because now they are anti to each other and in the same plane. That is very, very important, so that the elimination takes place, and what we observe is we get a product which is something like this and a CH3 and not this type of product. Although this is a very much stable alkene, this is a substituted alkene and this is not stable as compared to this, but still we do not get this alkene but we get this. This is sometimes also called an Hofmann product, comparing the logic from the previous Sedgwick and Hofmann, but remember this is E2 mechanism, that was E1 mechanism. So we get a Hofmann product which follows from the geometry or the symmetry of the molecule. This is not due to the stability of the product, this is because of the condition which is based on the E2 mechanism, that the hydrogen and the chlorine must be anti to each other. This is a very, very important concept and please take note of it. We will be doing many questions in which this concept itself can give you the answer. If you are good and if you have understood this concept well, then you can solve any question. For as an example, CCCC propane, we have a bromine here, phenyl here, 1,2 diphenyl. So this is the compound we have, 1 bromo 1,2 diphenyl propane. So now if from here I want to do the E2 mechanism, I want to do the dehydrohalogenation, what the product I will get? What is the product that I will get? So let us see here. For this we need to make sure that the hydrogen which is available over here, as you can see that there is exactly one hydrogen which is available for the bonding or which is available for the reaction, for the E2 reaction, that is the basyl abstract with hydrogen, and you will get a double bond. Fine, but we need to ensure that this is anti to this in the structure, and then only the base will abstract the hydrogen from there. So for ensuring that, we need to draw the 3D projection of this and then we can ensure. And for simplicity, we will take the Soh's projection. So this is one carbon, the first carbon, which contains the hydrogen, which contains CH3 and which contains pH, connected to this carbon which contains a pH and which contains a bromine. Now as you can see that this thing does not contain the H and the Br in the anti position. So let us bring it in the anti position so that the elimination is favored. For that we need to rotate this thing, or instead of that we rotate this thing, so that it will be easier for us to visualize. So if Br is here, that means H should be on the other side. For simplicity, let us rotate it. H comes over here, H comes something like this, and here we have pH and here we have CH3. Now this pH we can rotate it and bring it in this manner. Br is this way and pH is this way. Fine. So we get the H and the Br in the anti position. Now what do we do with this structure? What we do is we just eliminate the products. So that means this pH and pH, this CH3 and pH are on this side and this pH is on the same side as that of this pH. So here if you do the elimination, you get C double bond C, pH, CH3, because now this carbon will become planar and this carbon too becomes planar. This pH is down So what will happen? This will just come up. This will be pushed down and that will be just coming up. And there is a hydrogen here which we are missing. We can just draw it like that, that is not a problem. So we get particularly a cis alkene. What do you observe here? That if you have this stereochemistry earlier inside the reactant, then you particularly get a cis alkene. Now as you can see that this carbon is chiral, this carbon is also chiral. Now and definitely there is no plane of symmetry over here, because you can see that Br is there, CH3 is there, so there is no chance of plane of symmetry. So if you take a diastereomer of this, for example, if we have pH over here and CH3 over here, pH over here, CH3 over here. Now if you do the E2 elimination for this, what is the product that you get? The product you get is pH like this, pH like this, CH3 like this, and H like this. So now you get a trans product. So you see that the reactant or the products completely depend on the initial reactant. Suppose this was some R configuration or this is some S configuration. If you start with this configuration, you get this, and if you suppose reverse the configuration of this, you take a diastereomer, you get a transalkene. So you see this is a very stereospecific reaction. That is, if you want to get cis alkene, you need to start with this. If you want to get transalkene, you need to start with the diastereomer of this. Although there are so many diastereomers, there are totally 4 diastereomers possible for this compound and 2 enantiomers also. So that means we can get from all those 4, from some of them we can get cis, from some of them we can get trans. So it is not that stereospecific, but still this is quite specific. Fine. So as you can see that the anti-condition is very important in the E2 elimination. So here we have completed the elimination of hydrogen halides. Now let us move on to the second process. What is the second process? Second process is the dehydration of alcohols. The second process in the preparation of alkenes is the dehydration of alcohols. The dehydration of alcohols, and to be more specific, this is the acidic dehydration. That is, if you take any alcohol, something like this, then and if you treat it with the acid H2SO4 and heat, then what product you get is an alkene. And we can also know what is the mechanism for this reaction. The mechanism for this is the formation of a carbocation. This reaction involves the production of an intermediate, and that intermediate is a carbocation. Let us see how that happens. The reaction is quite simple. You have just the elimination of H2O molecules. If you compare the molecular formula of these two, you will observe that if you eliminate H2O from here, you get an alkene. Fine. Now, mechanism. What do you think is the possible mechanism for this? And definitely, if this has got a mechanism, this will have different transition states. So, what affects the stability of the transition states? For that, if you draw the potential energy diagram, you will observe that there is intermediate, and on that intermediate, what happens is, first this gets protonated, and if this gets protonated, this becomes a very good leaving group, and this leaves as water. OH, positive charge, and hydrogen. This leads to the production of a carbocation. So again, in this is a rate determining step. We won't be discussing much about this because this is quite the same as our alkene, the dehydrohalogenation case. But there, the more specific thing was when we have got E2 elimination, we get the stereospecific products. That was a very important point. But here, it is almost always observed that the formation of carbocation takes place So it kind of follows a even mechanism, that is formation of carbocation and then the abstraction of this hydrogen or the beta hydrogen by a base and then the formation of an alkene. So that means the same factors which affect the stability of the even mechanism or the even intermediate, that is the stability of carbocation, will affect the production of alkenes from alcohols also, because stability of carbocation. If the carbocation is more stable, then the reaction will be faster in their direction and then the product will be controlled by the stability of that. As an example, okay, and this intermediate diagram, we can have something like this. This is our original reactant and product. This is the carbocation that we get. This is quite same as the even reaction. Now, I want you to write the product for this reaction. The reactant is a 5 carbon molecule, 5 carbon ring, and sorry, this CH3 is not here. We have got a CH3 here and we have got a OH over here and CH3 over here. Now if this is subjected to H2SO4 and heat, what do you think will happen? Clearly this is a case of acidic dehydration of alcohols, and that means this follows the even mechanism. Formation of a carbocation, H plus from here protonates this oxygen and then this leaves as a leaving group, giving us this carbocation. So we get CH3, C plus and CH3. Now what do you think is the possible rearrangement that can happen here so that it stabilizes the carbocation? If this CH3 group shifts over here, it's of no use because we get some intermediate like positive charge, carbon, carbon, carbon. Here this is a tertiary carbocation, here it was a secondary carbocation. But okay, there is some use but not that significant. We can have a much more better stability to this carbocation if we just do one thing, that is if we take this electron density and shift it to this carbon, that is this electron density goes over here and this carbon donates or supplies the electron to the carbocation. Then what we get is this bond is broken, so we get 1, 2, 3, 4, 5, 6 membered ring with a CH3 over here, a carbocation over here and a CH3 over, this CH3 was here, next to it is a carbocation and a CH3 over here. And now which hydrogen do you think is eliminated? It is obviously this one, because again the Set-Jeff rule is followed. The more stable alkene is produced. If you halogenate or remove this hydrogen, then you get this alkene, but if you remove this hydrogen, you will be getting this kind of alkene, which is a highly substituted alkene and a very stable product. So Set-Jeff rule says that that must be the major product of the reaction. So as you can see that there is a ring expansion over here from a 5-membered ring to a 6-membered ring. That means it is a more stable product, and the stability gained by that is more than the stability gained by just this. And we see that the more stable alkene is produced because this alkene is highly substituted because of the presence of these two CH3 groups. Now another simple question. What do you think is the order of ROH, RC, COH, RC, CC, COH? Primary alcohol, secondary alcohol and tertiary alcohol. What do you think is the order of reactivity of these three when it comes to the dehydrogenation? But obviously that depends on the stability of the carbocation, and due to hyperconjugation and inductive effects, tertiary carbocation is more stable compared to the secondary one, and which is in comparison more stable to the which is more stable in comparison to the primary one. So that means this is the order for the acidic order, dehydration order, and we require very mild conditions for the dehydration of this, while very strong conditions, very strong concentration of acid and very high temperature for the dehydration of this. Now let us see the last preparation method, which is very much same as the dehydrohalogenation, which is called the dehalogenation. So it is dehalogenation of obviously dihalogen compounds. Dehalogenation of dihalogen compounds. That's a very similar reaction to the dehydrohalogenation, but the difference that it follows only the E2 pathway. And for an example, let us take dehydrohalogenation. So we need something called vicinal dihalides. If two haloatoms are present on adjacent carbons, those type of halides are called vicinal dihalides. And this, when they undergo the reaction for E2, here also we require a base, and here we take NaI. And when we take a base over here, what we get as a product is this. It follows the E2 mechanism, that is a bimolecular reaction. In the order of the reaction, the intermediate or the transition state will come, that is the I minus plus the halide molecule. So if you increase the concentration of the base, the reaction, the rate of the reaction will increase. Similarly, if you increase the concentration of the halide, then definitely the rate of reaction will increase, because the more the number of halide, it will be the more number of base molecules will be colliding with the halide molecules, and the more will be the probability of formation of the alkene. So these were the elimination reactions which we have studied, which are used to produce alkenes, and we have studied the various aspects of regioselectivity and stereochemistry of the reactions. Fine. Now moving on to the next part of the lecture, that is the properties or the chemical properties of alkenes. Chemical properties of alkenes include the addition reaction, the electrophilic addition reaction, which occur due to the pi bond density which is present over alkenes. If any electrophile is approaching the alkene, then the alkene can donate this pi electron density into the electrophile and can form bonds. And because the sigma bond is more stronger than the pi bond, that favors the reaction to go in the forward direction. So the electrophilic addition, now we have different variety of electrophiles available to us which react with alkenes to give different products, and all of them have got their typical stereochemical aspects based on the mechanism they follow. We will study some different types of mechanisms over here also. We will see basically all of them involve the production of an intermediate, but the stability of the intermediate, the structure of the intermediate, all of that depends on the reaction, what type of reactant we are using and what type of electrophile we are using. Addition on alkenes. One type of reaction is based on the hydrogen halides or HX. Second type, now this is just the opposite of the dehydrohalogenation reaction that we have just now seen in the elimination reactions part. Another type is addition of H2O, again opposite of the acidic dehydration of alcohols. Then third part is H2SO4. This gives you alkyl hydrogen sulfates. Then we have another something like B2H6. This is called diborane, and this also reacts with alkenes in different manners. Next we have CCl2, which is a carbene. This reaction is very important because this is an electrophile and we have a double bond, so this can give you some reaction, and this is a very stable intermediate or stable agent. So generally this reaction is very rare. I mean, the reaction conditions have to be very strong for this reaction to occur. Next we will have X2 in CCl4 and X2 in water. What is the difference between these two? We will see when we go to the reactions. Now this is the electrophilic addition on alkenes, but we have another part on oxidation of alkenes, where we will be studying the reaction with KMnO4, OSO4 and the ozonolysis of alkenes. That is very important if you want to identify what is the structure of the alkene. We know we can have many isomers for a particular alkene, and if you want to find out what is the exact structure of the alkene, then ozonolysis is the best method. So let us start with electrophilic addition on alkenes or HX, that is a hydrogen halide. Now what causes this reaction? We know we need an electrophile for this reaction. So where is the electrophile over here? HX. Now remember that we have a delta positive charge over here and delta negative charge. That means this hydrogen itself can act as an electrophile. So this goes and this goes. The pi electron density can be shifted to that hydrogen, and this bond will be broken in that case, and the intermediate which is formed is this carbocation, and the hydrogen goes plus X minus. So now again we see that there is a formation of carbocation. In this reaction, if you want to get a particular alkyl halide, then this is not a very good method, because this involves the formation of carbocation, and we know that for the carbocation stability we can have different carbocation rearrangements, and if rearrangements happen, then the original structure is destroyed and we get a completely new structure. So if you want a particular halide, suppose halogen over here, then this might not be the best method available. So now what about next? Next what happens is this halogen just goes and attacks this carbon. Now here comes the very important point. We know that carbocation is a planar molecule or a planar structure. This is carbocation with p orbitals this way. I will draw it in different colors. This is the carbocation and this is the p orbital. So now this X minus can attack from bottom or it can attack from top. From both the directions it can attack, and if all the three groups are different over here, R dash, R and H, then we get a enantiomeric pair. Why? Because if X attacks from top, we get a different stereochemistry. If X attacks from bottom, we get a different stereochemistry. And the probability that it will attack from top or from bottom is 50%. That means we get an racemic mixture and not a pure optically active compound. Because of the probability is 50-50%, we get a racemic mixture. 50% of the molecules, the X minus will attack from top, and 50% of the molecules, the X will attack from the bottom. So hence, in that way we will get a racemic mixture. Next, this was simple hydrogen halide. But suppose this carbon cation is formed over here, we know, and so the halogen will be coming over here. The final structure of the halide would be X over here and the groups like this. But suppose I want to get the X over here itself, that is on the terminal carbon. Here the X is coming following the most stable intermediate rule, and that is also called the Markovnikov rule. Now this rule says that the most stable carbocation would be formed, and to be the most stable intermediate, it can rearrange to get even more stability. That is the modern statement of Markovnikov rule, and that we already know that why should it form the most stable carbocation. But now my earlier question, how can you get the halogen on the terminal carbon? Because according to Markovnikov rule, this terminal carbon cannot get the halogen, because definitely this is a primary carbon, and suppose you have another carbon over here, then this carbocation will be more stable than the terminal carbocation. For that we have a solution. What we do is we add a peroxide. We use these organic peroxides to get this kind of halides. How do we do that? We do that by using the chemistry of radicals. You remember how alkenes react with chlorine to give chlorides? The same way these alkenes also will react with chlorines, or not with chlorines, with bromines, and bromine alone with HBr. That is, if we take this plus HBr in presence of peroxide, then we get some compound like this. That is, we get the anti-Markovnikov addition. So again, only HBr gives this kind of reactions, but not HCl or HI or HF. And HBr in normal conditions, if you take without the use of peroxide, then you will get the normal Markovnikov product. How do we get this product? We see the mechanism for this. Now this compound plays a very important role, which is a peroxide, because it contains a peroxy linkage or a single bond between oxygen and oxygen. So again, just as a free radical reactions, we have initiation steps. Initiation, what happens is this ROR converts into RO free radicals. That is, this bond is quite weak and it can be easily broken by application of heat or light, and we can get some RO free radicals. And then what happens? This HBr plus RO free radical gives you ROH plus Br free radical. So our free radical for this reaction is generated. So next what do is we go for the propagation steps. We have got the initiation, now let us go for the propagation. Propagation, if you write, we take the alkene plus Br free radical, that gives you, now this alkene can be, this pi bond can be broken homolytically and you get a carbon free radical. And again, which free radical will you get? You will get the most stable free radical, that is, you will get this secondary free radical. So C Br and this way. So now you see how we can get the halide on the terminal carbon. That depends on the stability of the free radical. If this free radical was more stable, then you wouldn't have got the bromine on the terminal carbon. And now we have got the bromine on the terminal carbon. We just react with HBr because that is the reagent that is present in our mixture, and we get the hydrogen over here plus Br here and Br free radical. So our free radical is again regenerated, and similar to the alkanes case, there will be some termination steps here, like this free radical combining with a free radical of its own type, or the Br free radical combining with another Br free radical to give Br2. So these can be the termination steps, and hence this can have a limited yield only. So this is in the peroxide case. So this was the case with hydrogen halides. Now we move on and remember the stereochemistry of hydrogen halides. That is, if planar carbocation is forming, the halogen negative charge or the negative halide ion can attack from top or from bottom, and we get a racemic mixture if three different groups are present on the carbocation. Now we go for the next reaction, which is the reaction with H2SO4. Now how come H2SO4 be an electrophile? Because with reaction with an alkene, we need an electrophile. So let us first generate a electrophile from H2SO4. The structure of H2SO4 is OH and OH. Fine. This is H2SO4. We have normal alkene over here. So how can you dissolve this alkene in H2SO4? We can dissolve that by this positive hydrogen. We know this is an acidic hydrogen, and hence the electron density can be donated to this, and obviously the carbocation, the most stable carbocation, will again be forming over here. Here we don't have anything called the E2 mechanism. Here everything proceeds through the carbocation intermediates. Although we will see a different kind of intermediate in case of dihalogens, that to X2 in CaCl4. Fine. So we get a hydrogen, we get electrophile, and this becomes our nucleophile, or the X minus, the role of X minus is now played by HSO4 minus or OHSO3 minus, because this O will go and attack that carbon, that carbocation, and we will get a structure like HSO3 C and C. This is called hydrogen sulfates because of obvious reasons. This is a HSO3 group present over here. So this is also a very simple reaction, and this on hydrolysis on H2O can give you alcohols. So that means ultimately the end product is alcohols and not this. And if you can eliminate H2O from this mixture, that is only pure H2SO4, then the final product will be alkyl hydrogen sulfates. Fine. This is also a very simple reaction. Now let us come to the alcohol or the reaction with water. The two major reactions over here are the reactions with water and the reaction with dihalides, because there a specific stereochemistry is followed, and we will see how it is done. Wait. So we have an alkene, we have water, and we take an acid. Now over here we can have the addition of water in three different ways. I mean, once if you use the reagent as an acid, another case if you use the reagent as HgOSC twice. That is, this is the acetate group CH3C. This group, the acetate means O minus. This is called the AC group. So ACO minus twice, that means this must be Hg2 plus. So this is this kind of ion, OAC minus and Hg2 plus. But this is the second type of reagent. The another reagent can be BH3 H2O2 OH minus. Now this is called oxymercuration demercuration reaction. This is called the hydroboration oxidation, the product of all the three reactions, and this is simply acid catalysis. The product of all the three reactions is simply the production of alcohols from alkenes, but with different and varying stereochemistries. In this acid creation, there is no particular stereochemistry because of the mechanism followed. The mechanism is normal carbocation intermediates, and you can have rearrangements and all sorts of stuff here. Nothing new, but we will see some two new things in the coming two reactions. So alcohol is there, water is there, electron density we have. So where is the electrophile? The electrophile is generated when you react this H2O with H plus. When this H2O is reacted with H plus, you will get H3O plus. And now this is exactly the electrophile which is required for this addition. So C plus H3O plus, we can write it this way. Now this oxygen has got the positive charge, but that atom is not the electrophile. The electrophile is the hydrogen atom, because this is just a kind of formal charge. That oxygen is not deficient of electrons, its positive charge is the formal charge, and so the electrophile will be this, and the electron density will shift here. Oxygen, even though it has got a positive charge, has got a pair of electrons, hence it is not an electrophile. Fine. Now we have got the first step of a reaction, that is the creation of carbocation. So carbocation created, plus we have the H2O molecule. Now what next? We need to attack this carbocation because this is an unstable species, and obviously rearrangements can occur, no doubt about it. I have shown you two kinds of rearrangements. One is the normal methyl shift, another one is the ring expansion. You remember where the 5-membered ring expanded into the 6-membered ring. So now from here, how do you continue? Or not exactly from here, from here. We take the oxygen lone pairs. Oxygen also has got some lone pairs. We will donate it into the carbon ones. So we will get a positive charge on oxygen and carbon like this. So those two have combined, and oxygen has donated its lone pair into this carbonium ion. Now what next? We take another H2O molecule and we abstract this hydrogen. So we can get alcohol. Now again carbocation is a planar molecule, so you can have different stereochemistries here, but no particular and specific stereochemistry. In case of hydrogen halides also, we can have any stereochemistry and not a particular stereochemistry. So what is our final product? Final product is an alcohol. simply this hydrogen abstracted and H3O plus is again reformed. That means H3O plus starting of the reaction and in the end of the reaction, that means it acts as a catalyst. Fine. That is why it's called acid catalyzed electrophilic addition of water on alkenes. What next? Next is the oxymercuration, demercuration. Now that is some good stuff. Oxymercuration, demercuration gives you a Markovnikov product but with no particular stereochemistry. So if you want a Markovnikov product, go for oxymercuration, demercuration because it gives really high yields without any rearrangement. That is a very, very important advantage because if you want to produce a specific alcohol from a specific alkene, then you want to go for the oxymercuration, demercuration case because there the rearrangements don't happen. We can control the reaction. So let us see how the reaction happens, or let us first see what is the overall reaction. Overall reaction is if you react this alkene with HgOAc twice and we require here NaBH4 and OH minus. So first step is the HgOAc twice and next step is the NaBH4 and OH minus. What is the product? Product is the Markovnikov addition of alcohols over here like this with no particular stereochemistry but without any rearrangements. This happens without any rearrangements. That is, if you have that earlier pentane molecule, cyclopentane with this CH3 with alcohol and this CH3, then here if you take this alkene if you go for normal acid catalyzed hydrogenation or the addition, electrophilic addition, you will get a carbocation here and again the same rearrangements will take place, that whole ring expansion will happen and you will get some structure like a carbocation here and one CH3 here and one CH3 here. But if you go for oxymercuration, demercuration, then in that case this alkene will give you specifically this alcohol and not the rearranged product. So that is exactly the advantage of this reaction. Let us see a small mechanism, it's not very big, a very simple logic. What happens in the first step is this HgOAc twice distributes into Hg plus and HgOAc plus, something like what do we write here? OAc minus plus HgOAc plus. So it distributes into this kind of structure. Next, what is a possible reaction? We have got an electrophile. That means we can take this pipe on electron density and just like that donate it over here. Here again this carbocation is formed, but with a slight difference that this carbocation is now having a partial positive charge. Why? Because of the HgOAc group. This mercury atom actually stabilizes the positive charge and takes a partial positive charge on itself. Mercury is a metal atom, so positive charge is stable on the metal, and it kinds of form this kind of intermediate. Now next what happens? Now because of this intermediate, because of this partial positive charge, this is not a proper carbocation and hence it cannot rearrange. And now the story is the same. You have water molecule, OH minus comes, OH minus attacks, and we get OH on this side of HgOAc. That's it. Now you can observe that although there is a specific stereochemistry over here, that is the OH is attacking on the side anti to HgOAc, but the point is after this is the mercuration step, oxymercuration step, but in the demercuration step what happens when we react with NaBH4 and OH minus, the whole stereochemistry is scrambled because of the production of radicals, because this does not undergo normal carbocation or carbon and intermediates, this undergoes the radical intermediates, and hence the whole of the stereochemistry is scrambled, and we don't get a particular stereospecific product. Although over here the OH is attacking anti to its HgOSC, so what you will expect is the hydrogen also coming to be anti to the alcohol. But the point is, after this the whole stereochemistry is scrambled and we get both syn and anti additions. Are you following it? If you are not, then please rewind it, because this is the most important part in this reaction, that why we do not get a particular stereochemistry in case of HgOSc, that is the oxymercuration demercuration case. Now simple, after this demercuration you get some kind of alcohol like this. And as I have already given you an example with the previous example, that without any rearrangements you get the initial alcohol back from which the alkene is produced. So now this was oxymercuration demercuration with no rearrangements but with no particular stereochemistry. Now we are going to see the hydroporation oxidation one, that has got a very specific stereochemistry, and a more important point than that is it is an anti-Markovnikov addition. That is, you don't get most stable alcohol or the most stable carbocation. That is because you don't get a carbocation in this case. The thing is, if you take something like this, one propene, this is our alkene, and you treat it with BH3, then what happens is all these three hydrogens are replaced by three molecules of propene in this way, B, C, C thrice. That is, this double bond is broken and you get some kind like that. So if you want to get an alcohol over here, now that is very much possible. There is no possibility of any carbocation over here, and you directly get an alcohol over here, but with a particular stereochemistry, that is, the alcohol and H will be syn to each other. Now how do I explain that? I will just complete the reaction first. Now the reaction after this is very simple. We take BH3. It is very important that you use a non-polar solvent or at least tetrahydrofuran. Now we have got this nice structure, then we take oxidation of this. That is, we oxidize this structure with the help of hydrogen peroxide in basic medium. That gives us the alcohol this way and hydrogen this way. That is the anti-Markovnikov addition. You are getting the alcohol on the terminal carbon, which is not possible with oxymercuration demercuration or even the acid catalyzed hydration. So, and the specific stereochemistry is that you get a syn addition. That is, you get something like this. As an example, you can just take, this is pentane. If you have an alkene over here, you have a CH3 over here, then you get, suppose, an OH in the bottom, because this is an alkene, so we can get an OH on the top or on the bottom. But if we get the OH on the bottom, then the top position is already occupied by the CH3, so that means now we can get only, if we get an OH on the top, we see that the OH is top position is already occupied with CH3, so hydrogen cannot come there, and we know that by the stereochemistry of the reaction, that the reaction produces syn addition of H and OH. That means this OH can come only at the bottom, and this hydrogen will come like this. So we get a syn addition of H and OH in case of hydroporation oxidation case, and you see the stereochemistry and the anti-Markovnikov addition over here. Two very important points and very helpful reaction in producing primary alcohols, because they are not so easy to produce from alkenes because of the stability of intermediates or carbocation. Now let us see how dihalogens react with alkenes. That is, reaction of Br2, Cl2, etc. etc. We have an alkene and we have Br2, suppose. Now we need an electrophile as usual. So how to generate an electrophile? From where can the electrophile come? The electrophile has to come from this bromine atom itself. This bromine gets a positive charge, this gets a negative charge. This is not due to the dipole moment, this is due to, because it wants to participate in this reaction, this carbon electron density, the pi bond density can be donated over here, and this can be taken by the bromine. So now here there is no formation of carbocation exactly, because here the electron density cannot be fully donated to the bromine. It does not have that much dipole moment that it can be donated into that completely. So there is a intermediate, a different kind of intermediate, which is something like Br, C, and we have got a positive, delta positive charge over here, and delta positive charge over here, and Br minus as usual. Now, so once the electron density is donated into this, we get an intermediate like this, and this 4 groups normally. Next what happens? Next we have this Br minus, which now acts as a nucleophile. That means it seeks a electron deficient center, and hence it attacks this carbon, and it attacks in such a way that it is anti to this bromine. You observe that this bromine cannot attack this carbon on the same side, from the same side as this bromine Br delta positive charge is present, because there will be so much repulsion. Suppose this was the earlier alkene, now the bromine has come here like a triangle. So the bromine is here now. Bromine is over here now. Now the another bromine, it cannot come from the same side and attack this carbon. This carbon has to be attacked from the opposite side or from the top. So when it attacks from the top, you get an anti-stereochemistry over here. So the stereochemistry over here is very, very important. You get a anti-product over here, that is C, you get a Br like this, and you get a Br like this. So this is a very, very important reaction of halogens, that when they are reacted with alkenes, they give the anti-product, and this plays a very, very important role in the stereochemistry of the reaction. Suppose you take transbutene and cisbutene, and suppose you take cisbutene. Now if you react this with Br2 in CCl4, this is very, very important that CCl4 should be present and not any water or any other polar solvent. Then in that case, this type of intermediate will not exist, and you will get the normal halohydrine, or the reaction which you are going to see next. There a formation of positive carbocation is possible because we have a polar solvent. Here we didn't have any polar solvent, so it cannot solvate the carbocation, and hence it cannot protect it, or it cannot stabilize it. So that means this CCl4, because of this CCl4, we get an anti-stereochemistry. Otherwise we would get a normal carbocation, and then in that case anything is possible. Anti-addition also, syn addition also. But syn addition is very difficult here because of the size of bromine. If the size was small, then syn addition was possible. So even in that case where the carbocation is forming, anti-addition is the most dominant product. So what we were discussing was what is the product for transbutene with Br2CCl4. You get two bromines such that this bromine is on two opposite sides, and the two CH3s and two hydrogens. Now if you take a mirror plane which is passing like this, then you will see that that is the plane of symmetry for this molecule, because trans was already opposite, the CH3 was opposite. Now you have added in the same opposite fashion Br also, hence you will get a racemic mixture, or a meso compound, because it has got a plane of symmetry, although both carbons are chiral. So that means with this you must get a racemic mixture. Why? Because here the two CH3 is on the same side, and you add two Br on the opposite side. hence creating a asymmetry in the molecule. And since you have got an asymmetry in the molecule, you have got two chiral carbons, and now what is possible is, suppose Br attacks from up, this attacks from down, you will get another one stereochemistry, and if Br attacks from down and this Br attacks from up, you will get another stereochemistry. But the point is that both will be enantiomers of each other. You won't get diastomers in this case because the two Br2 are always anti to each other. They are always added anti. So if the configuration at this carbon changes, this carbon also reverses. So you get an enantiomeric pair, and again you get a racemic mixture. You still do not get a optically active mixture because you cannot get the pair of diastomers here. You will always get pair of enantiomers. So this was a very important reaction because of the stereochemistry of the reaction, and the stereochemistry comes due to the CCl4. If you use water, that is, you get a halohydrin, which can be seen in this way, that the halohydrin would be positive charge Br. Suppose you take Br2 in water and you start with this. Now when this happens, normally Br plus and Br minus will be formed. Br minus will come over here, but now this positive charge will not form any triangle structure because now this positive charge is actually supported by the water molecules and it is completely solvated. Now hence the OH minus comes, attacks this carbocation, and we get our halohydrin, which is called so because of the halo group present and the hydrin or the hydro group present. So this was a reaction with Br2 and H2O. So you see that just by changing the solvent, we have changed the product. That is, this H2O, this OH and Br can also be syn. If we use suppose Cl over here, then it is possible because Cl size is small and OH also size is small. So that will also be not be a major product in that case also, but relatively the amount will be higher. The major product will always be the anti-product because the minimum repulsion case. Repulsion is minimum in anti-case. So this was the addition reactions on alkenes. Now let us see some of the oxidation reactions. One addition reaction is still left, that we will discuss after the oxidation reactions. So first oxidation reaction of alkene is with aqueous KMnO4. Now with KMnO4, alkene has got two reactions. One is with aqueous KMnO4, one is with very strong KMnO4. With very strong KMnO4, it just oxidizes completely, and with aqueous KMnO4, you get a dihydroxylated product. So it is no more electrophilic addition. We have oxidation. We have oxidation of alkenes. So in oxidation of alkenes, we will be seeing first the reaction with KMnO4, aqueous, and one more reaction with OSO4 and sodium bisulfite, and reactions like ozonolysis and reaction with complete oxidation of alkenes. We will see how we can completely oxidize alkenes. So these are the few reactions that we are going to see under this oxidation topic. Now first of all let us do the reaction with KMnO4 aqueous. Suppose you take this alkene and you react it with KMnO4, but remember the KMnO4 should be aqueous, it should be a dilute one. If you take a strong solution of KMnO4, then you would completely oxidize the alkene. And oxidizing alkenes means, what is the oxidation level of alkene with respect to alkenes? Alkenes is actually almost same oxidation level, because if you calculate the oxidation state, it comes out to be +4. But if you calculate the oxidation state in carbonyl compounds or carboxylic acid or carbon dioxide, it is quite different. So that means it is oxidizing, that is addition of oxygen or removal of hydrogen. Carbon dioxide is the most oxidized product, then we have carboxylic acid, then we have aldehydes and ketones, then we have alcohols, and then we have alkenes, alkynes and alkanes. Now with aqueous KMnO4 you just get the alcohol oxidation. That means the oxidation is mild oxidation and you get 2 alcohols here, but not 1. So you get a syn addition. This is a very important point, that the alcohol addition has to be syn. Again, with respect to stereochemistry, this can change a lot of things. That is, you get a racemic mixture, you get a meso compound, or you get diastereomers. Everything depends, because here we have got a stereo-specific reaction, a syn addition, similar to that of hydroboration and oxidation. So suppose I take a specific example. These examples are very clear with if you take cyclic compounds, because cyclic compounds you can easily identify which is up and which is down. So if you take and react this with KMnO4 aqueous, then what you get is this alkene, and you get one OH this way, another OH this way. You get a syn addition of both the OH groups, which is also called dihydroxylation. Now this can also be achieved by another reagent, which is called the osmium tetroxide. Osmium is a very important element in inorganic chemistry, because you know it has got very heavy density, or the most dense element in the periodic table. OSO4, osmium tetroxide, followed by hydrolysis with bisulfide, or you can have here hydrolysis with bisulfide. Fine. Now when you have this reaction, you get the same products also. Again the syn dihydroxylation of alkenes. Same reaction, OSO4 and NaHSO3 minus H2O, you get the same product as you get with KMnO4. Now this way is more better, because KMnO4 can also completely oxidize the alkene. Even if you take a dilute solution, it might be possible that most of the alkene is converted into this and some is wasted in the complete oxidation of alkenes. That means this can be oxidized to ketone groups. So now we have completed the dihydroxylation. Now let us go for strong oxidation. What happens when these alkenes are subjected to very strong oxidation of KMnO4? And then we will study a very important oxidation reaction of alkenes, that is the ozonolysis. It is also very important with respect to finding out the proper structure of alkenes. What was the original structure? So let us see with KMnO4, if one alkene like this is reacted, I can take CH3 again. Now if you react this with KMnO4, now here there is no more dilute solution, you have a strong solution of KMnO4. Then the product you get is, wherever the double bond is there, that will be cleaved, and you get, suppose here you get an aldehyde and you get CC double bond OH. Now with this information you can also identify whether, now this is just one oxidation, one step oxidation, that is the double bond will convert to OH, first alcohol and then aldehyde. Now this can further be oxidized because there is a hydrogen over here, and you can write propanoic acid over here and C ethanoic acid over here. So these will be the products of complete oxidation of this alkene. Now with that information, can you identify what is the structure of this alkene? Yes, we can definitely identify, because what we need to do is just join these two carbons with a double bond, because we know if these two were joined by double bond, then if you break them, you will get two carboxylic acid groups in the end. Another simple example can be this. Now this, if you react with KMnO4, what do you get? You get 2 moles of carbon dioxide directly. It is completely oxidized. You won't get here acetic acid or anything. You will directly get carbon dioxide. So this is a very important reaction because it is we can find out the structure of the original alkene. Now the same thing is there for ozonolysis, but in ozonolysis the oxidation is not complete. The oxidation stops at the aldehyde or ketone level. Now ketone, how can it be produced? You have seen here ketone. Suppose I have a double bond like this. If I get a carbon which is having OH this way, only with only one hydrogen, then in that case what happens is this OH and H will be converted to double bond O, and this further cannot be oxidized. That is quite understood. Why? Because this is a ketone. Now ketone, if you get, that is a maximum oxidation level. This carbon has got no more hydrogens and hence it cannot be oxidized. So if you have some terminal alkenes, then you can get carboxylic acid and ketones also. Fine, this was KMnO4 oxidation. Now let us go for ozonolysis. If you go for ozonolysis, what are the reagents first? That is very, very important. And in ozonolysis, one important intermediate forms, that is called ozonoid. That has got a typical structure. We will see it just now. So if you have ozonolysis like this, now you take an alkene, you put some reagents. You use O3 here because the name suggests that the reagent must be ozone, and then you have Zn, H2O and acetic acid, OH. Fine. Now when you have this much reagents, we will see the role of these one by one. Now first of all thing, what does this ozone do? Now we need an electrophile for the double bond to react, and ozone does exactly that. Obviously you can identify that why this Zn is present, because if you react directly with ozone, then it will be oxidized completely and you will get the carboxylic acid. But if you put some Zn there, the oxidation will stop at the aldehyde or the ketonic stage. So we have C double bond C. This will be broken, this structure, and a new structure forms, which is something like this. So it's alkene reacting first with ozone will give you some this kind of structure. This is called the ozonide. Now this ozonide, what happens to this is it undergoes some rearrangements. The mechanism we are not discussing over here is not relevant to JEE syllabus. So it undergoes some rearrangement, and what we get finally is a cage-like structure, which is something like this. This is called the mole ozonide structure. And after this it is very simple. You have complete oxidation of this structure, that is this bond cleaves, this bond cleaves, this bond cleaves, this bond cleaves. That means with this and this you will get an aldehyde, because oxidation has to stop at a certain stage. You get an aldehyde, suppose R was present, R dash was present and hydrogen was present. Now you have R dash over here and hydrogen over here. You get R plus R dash C double bond O H. One carbon is present over here, another carbon is present over here, and because there are two bonds with oxygen, it will oxidize two times, once alcohol, another times aldehyde. And here also there are two bonds present, so once it becomes alcohol, and another time when it oxidizes, it becomes a aldehyde. Now suppose I replace this by an R dash group or R double dash group. Here I replace by R triple dash group. Then what I get is a ketone, and this ketone is a maximum oxidation state. And anyway, even if it is aldehyde, it does not convert to the carboxylic acid stage because of the presence of this Zn. Because of this Zn, the oxidation stops at the aldehyde or the ketonic stage. So this is the ozonolysis. Now, how can we identify the structures from here? What we need to just do is find out where the double bond are present. That is, wherever we are getting a carbonyl carbon, that means the ozonide oxygen must be attached at that position. That means that must be the site for the double bond, and you have to just combine those two and you get our original alkene back. So this oxidation with KMnO4 and ozonolysis both are very good methods for finding out what is the original structure of alkenes. Fine. So we are done with all the oxidation reactions of alkenes. But as I said you, there is one electrophilic addition reaction still left of alkenes, that is the dihalocarbene reaction. The dihalocarbene reaction, you get something called a ring, which is cyclopropane ring. The cyclopropane ring is obtained how? We will see in a moment. So reaction with dihalocarbene. How are these produced? First of all thing, how are dihalocarbenes produced? Or first of all thing, how are carbenes produced? Carbenes can be produced by using methane diazonium salt. Now this is called the methane diazonium salt, and if you heat it, this immediately decomposes into a carbene and nitrogen. Methane diazonium salt. You heat it, you will get CH2 carbene plus N2. Now this carbene has got this kind of structure, CH and CH. We have got triplet carbene, we have got singlet carbene. The singlet and the triplet terms come because of the multiplicity of the carbenes. Now this we will study further in quantum mechanics. We are not going to discuss that concept over here. We will move towards the reaction of dichlorocarbenes with our alkenes. So once we have known how do you prepare alkenes, how do you prepare carbenes, we can also guess how do you prepare dihalocarbenes. We need something which decomposes into like this, or when you have something like this, H minus should leave and should leave us with Cl2, this Cl2 and lone pair of electrons. So that means we need a leaving group, or in other words, we need what is called the alpha elimination. Consider the reaction which I am going to just write right now. We have seen beta elimination. This is the counterpart of beta elimination, the alpha elimination, which is used to produce the dihalocarbenes. So if you take CHCl3 and a strong base like KOH, then what do you get? You get CCl3 minus, because this KOH abstracts this hydrogen. Now what is alpha elimination over here? If there was some another carbon and another hydrogen, probably some beta elimination would have happened and Cl would have gone and H would have gone. But in this case what happens is the beta carbon is not present. So what do? You do an alpha elimination and the Cl minus leaves and you get a dichlorocarbene with a lone pair of electrons. And this is not, the octet of this carbene is not complete, as you can clearly see, only 2 bonds and 1 lone pair of electron. So that means it is only 6 electrons and not 8 till now. So hence it is a very reactive reagent and it undergoes reaction with alkenes. And why does it undergo reaction with alkenes? Because it is an electrophile. The octet is not complete. I have R dash, hydrogen, R dash, hydrogen. Now if I react it with carbene, that is the dihalocarbene, what is the product that I am going to get? What I get is a cyclopropane ring, and in this ring the stereochemistry is maintained. That is, the R and R dash groups, if they were trans earlier, they will remain trans even now. So R and R dash, hydrogen, hydrogen, and here we have the Cl bonds, Cl and Cl. So now these two are in the plane and this is above the plane, this is below the plane. But what is most important is the stereochemistry of the R and R dash groups. They are trans if they are trans earlier, they are cis if they are cis earlier in the alkene. So if you use a cis alkene, you will get a cis product over there. So this was the end of the alkenes reactions. Now we move over to the counterpart of alkenes, the alkynes. Alkynes, the reactions are very similar to alkenes except for the fact that it has got an extra double bond. That means whatever the alkene can react with, it can react with one more mole of that. So let us see. And other than that, there is only one special property about alkynes, and that is the acidic character of its terminal hydrogen. Terminal alkynes have got an acidic hydrogen directly attached to them. Suppose we have this alkyne, then this hydrogen is an acidic hydrogen. Why? Because this is not the case with alkanes and alkenes, but with alkynes. Why? The reason lies in the statement which I just made. This is not the case with alkenes and alkynes. Why? Because the hybridization of the carbon is sp3, sp2 and sp. And sp carbon is much more electronegative than the sp3 carbon or the sp2 carbon, and hence the carbon, the negative charge is more stable. And if you write, this will be the basic order because the negative charge is this way, and hence this will be the basic order is just the opposite, as we know, this way, and hence the acidic order is this way. That is, sp carbon is having more acidic hydrogens. The hydrogen attached to the sp carbon is more acidic as compared to the hydrogen attached to the sp2 carbon or the sp3 carbon. So that is one important property of alkynes, and that we can observe if we react with it amide ions. If we take liquid ammonia and sodium, then we get sodium amine, and if that we react with this alkene or alkyne, then we get this alkanide ion, we get this C triple bond C minus plus NH3. So that means that this is a stronger base than this, and hence it acts as an acid. This reaction is not observed with alkenes or with alkanes. This is a special property of alkynes, and this is used to actually purify the alkynes. Why? Because this negative ion can now react with heavy metal ions like Ag plus and Cu plus, and can get precipitated, and you collect the precipitate and you form the alkene, get the alkene back or the alkyne back, and you have purified the alkyne. Why? Because only this will precipitate, and the precipitate contains purely only the alkyne part and no other reagent. So that means this is actually a property which can be used for purification. And if you react with this U plus, then you get a precipitate which is red in color. Red precipitate you will get, and that can also act as a test for alkyne. Suppose you want to check whether the given compound has got double bonds or triple bonds, then you can perform this check. For double bonds, what you do is you perform the ozonolysis and you will easily get the solution, because ozonolysis of alkynes will give carboxylic acids, as you will see, but ozonolysis of alkanes will give only aldehydes and ketones. Now if you want to check for alkynes, then you go for this Cu plus test. You add some Cu plus solution, and particularly if you add this solution, CuNH3 twice, positive charge. If you add this complex solution to this organic compound, the alkyne, you will get a red color precipitate which shows that alkyne is present in this solution, or the given organic compound contains a triple bond. And we can also be sure that it is a terminal triple bond, because in between triple bonds have not got that hydrogens, they haven't got the hydrogens with them, so there is no point of acidic hydrogens. Suppose you have a triple bond here, then these carbons do not even have the hydrogens, so there is no point of acidic hydrogens. Fine. So this was the introduction to alkynes. We have seen the acidic properties of the terminal alkynes, but now what are the physical properties? Physical properties are quite the same as alkenes, except for the fact that alkynes are more polar than the alkenes, and hence the solubility is little bit more, but still the solubility is negligible as compared to other compounds like carbonyl compounds or the carboxylic acid, which in addition to the polarity have hydrogen bonding. These atoms, the alkyne and alkenes and alkanes, are pure hydrocarbons, and they have got no hydrogen bonding with water if they are dissolved in that, so they are very much soluble in the organic solvents. So physical properties also include the density. Densities are lesser than water. So that's it. That was the physical properties. Boiling points are quite similar to alkenes and alkanes. And what about the chemical properties? One of the major chemical properties is the acidic properties. Acidic property we have just now discussed. Now for further chemical properties, let us see what is the difference is between the structure of alkynes and alkenes. The basic structure is that alkynes contain a triple bond. That is, they have an additional pi electron density to that of alkenes. So whatever reactions we have studied for alkenes, if we do one more time the same reaction for alkynes, you will get what is the chemical properties of alkynes. For example, halogenation. If you can react Cl2, 1 mole of Cl2 with alkenes, you can react 2 moles of Cl2 with alkynes. So that will be the chemical properties of alkynes, but the acidic property is the only different property which is different from alkenes and alkanes. So let us start one by one. This is a very small topic because all the properties are similar to alkenes. But before going for the properties, we need to see the preparation. We have seen the physical properties, now we need to see the preparation. This is the order we follow for each and every group. We see what is the structure and what clues we can get from the structure about the properties. Then we see how it is prepared. Then we go for the physical and the chemical properties. So now the preparation, it can be prepared from an inorganic compound by this reaction. That if you take calcium carbide and react with and hydrolyze it, you will get C triple bond C plus calcium hydroxide. So this is another example where an inorganic compound is converting to an organic compound, and that to an alkyne, having 3 bonds or 1 sigma bond and 2 pi bonds. Second reaction can be, this is actually an old reaction. This is an industrial reaction, that is, it is used in industries for the production, for the large quantities of production of alkynes. This cannot be used in laboratories because this gives very, very less yield. But this is very, very economical, so they use in industries. Now, this is an old reaction, but the modern reaction is this. You take CH4 and you pyrolyze it. That is, you heat it very fast and you heat it at very high temperatures and you push it or you compress it very fast. In that sense, this methane will go under pyrolysis and produce this and H2. So very simple reaction. If you take 2 of this, you will get 4 molecules of hydrogen. So these two are the industrial processes. This is the old one and this is the modern process. This is a very cheap processes, that's why they take it in industries. But in labs, we cannot prepare these compounds. We cannot prepare the acetanilide or this alkyne by these methods because this require a lot of heat, which is not possible to generate in labs. Now, what are the laboratory preparations then? We definitely have some preparations for laboratory also. What we can do is, how do we prepare alkenes? What we take is, take a X, take a H, eliminate H and X, and you get an alkene. Same thing you do, but what you do is, you add 1 more X, and there should be 1 more H. So this is also vicinal dihalide, but this is the double dehydrohalonation. Double dehydrohalonation of vicinal dihalide will give you alkenes. Now, what about if I put X over here? That is, I put X over here and H over here. Now also these two can go undergo elimination and these two can go undergo elimination. Yes, that is also true, and these type of halides are called gem dihalides. So the gem dihalides also undergo elimination and they give you alkynes, but there is a difference in the two eliminations. Let us see what is the difference. The difference is, in the first case, even if you use a weak base, it is okay, but in the second case, that is when you have got an alkene and you have got a halide atom attached to the carbon atom of the alkene, then in that case you cannot use a weak base, you have to use a very strong base, otherwise the dehydrohalogenation cannot occur. Already this requires some amount of strong base, but now this second elimination requires particularly a very strong base. So one, if you take KOH also, fine, no problem. Then you will get C, X, this X and this H remaining. This X and H will dehydrohalogenate, fine. Now you need to use a very strong base, something like NaNH2, sodium amide, which is an excellent base and a very, very strong base. And then only you can get this type of structure called alkynes. So this was a laboratory preparation. What about dehalogenation of double dehalogenation of this molecule? That is, if you have 4 halogens over here, one halogen here, one halogen there, and one halogen over here. This we know is possible in case of alkenes. That is, if you have 2 halogens like this, then you can dehalogenate and you can get a double bond. Same case here also, you double dehalogenate and you get a triple bond. Same thing, and again you require a strong base in the second elimination. But this is not a very good way, because this way, the reverse of this process is exactly how we get this compound. That is, we take an alkyne, we go all the way backwards and we get this compound. So in order to produce this compound, we are using alkynes. So how can we use this compound to produce alkynes? This is not a very good way. So the first way was much better. Fine. There is one more way of preparation of alkynes, and that is by using alkynes itself. And that is by using the acidic properties of alkynes. Let us see how. We can use the acidic properties and generate the carbon ion like this plus NaNH2. What we get is this kind of ion. Fine, we know that. Now this thing, if we want to extend it, that is, if we want to add an alkyl group over here, what are our possible options? One very good example is, or one very good option is, you take a primary halide, or let it be something from here. This type of reaction we will study in the alkyl halide chapter. This is a typical reaction for alkyl halides, which is called a substitution reaction, and this is SN2 reaction to be specific. In substitution also we will have 2 kinds of reaction, SN1, SN2. Same difference between both, that one is unimolecular, one is bimolecular. Now with this, what we get is C triple bond C, X. Sorry, not X. X will be gone. That is, this will be nucleophile will be attacking R, and this X will go as X minus. So we get a R over here, and we can choose our R. So we can extend this alkyne to any number of carbons. What if I don't want to get a terminal alkyne? I want to get an alkyne somewhere in the, such that the triple bond is in the middle of the chain. No problem at all. What you do is, before going for this step, you do one more NaNH2. You treat it one more time with NaNH2. What will happen is, this carbon also will get the negative charge. So this carbon, negative charge, triple bond, and with the original carbon with the negative charge. Now you treat it with your favorite Rx. Now if you treat it with your favorite Rx, you get one R over here and one R over here. So finally you get a triple bond in the middle of the chain. For example, suppose R is CH3, then you get this type of alkyne with the triple bond at the second carbon. So you see that alkynes itself can be used to prepare alkynes, and in this manner. This is actually not the preparation, a kind of extension of alkynes. We are extending the number of carbons present in the molecule. Fine. Very simple preparation methods. Now let us see what are the chemical properties. Physical properties we have discussed, preparations again we have discussed, chemical properties. Now the chemical properties, again we will have here the addition properties and the oxidation properties. Addition properties very similar to the alkenes. That is, suppose we have HX, Cl2, Br2, all of them. Whatever properties you have for alkenes, same is there for alkynes. That is, HX is there, one molecule you take, you add it, you get this kind of structure. One more HX you add. As I told you, whatever reactions are there for alkenes, do it one more time for alkynes and you will get the product. So you get C, X, X, H and H. So you get gem dihalides with HX. Similarly with Cl2, you will get all the 4 Cls over here. That is, all the 4 atoms would be the halogen atoms itself. Halogen, 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 everywhere. Similarly with Br2. But there is a slight difference with Br2 when you do the addition. That is, if you use peroxide, as we have noted in case of alkenes, that this thing plus Br2 gives the anti-Markovnikov of product in the presence of peroxides. Similarly here also, if you take alkenes, suppose you take that example itself, if you take an alkene over here, then you will get Br2 over here. Or if you take HBr, you will get HBr, Br over here and hydrogen over here. So this type of product you will get, and this product does not undergo further reactions with HBr with peroxide. This is the only difference between alkenes and alkynes, or between the reaction with HX, Cl2, Br2 normally and Br2 peroxide. That Br2 peroxide is only one step, second step it will not go. Fine, job is done. We have discussed the addition reactions. So simply we have discussed addition reactions. In alkenes we have discussed this for so long time. We have discussed each and every aspect about stereochemical and regiospecific, stereospecific types. But here what we need to just do is do one more time the same reaction what we have done for alkenes. Alkene if you do it once, alkynes you do it twice. So this was the chemical properties of alkynes, but we will consider one reaction in detail because that is very different from the alkenes reaction. That is, if you take an alkyne this way and you take H2O, react with H2O in presence of HgSO4. When you react this in presence of HgSO4, then there is some important products that are forming and some important reaction. What do you think will be the reaction? Normally H2O will add over here, so Hg2 plus is already present. In addition to that, we are just mentioning that Hg2 plus is also present. So if you just do this, we get alcohol over here and hydrogen over here, and normally this carbon. Why? Because suppose this was alkene. What do you think will be the product? The product will be alcohol over here and hydrogen over here. But here see the difference. What we are getting is the alcohol we are getting on the end carbon or the terminal carbon or the anti-Markovnikov product. So that is the difference here between the alkenes and the alkynes. Here exactly in presence of HgSO4 and Hg2 plus, it reacts with water and produces some kind of structure like this. Now the intermediate which leads to this is very unstable because it is a vinylic cation. That is, it involves the formation of this kind of species. Why? Because OH minus, same mechanism as that of alkenes, formation of a carbocation and then addition of OH minus. So if carbocation is to be formed, it has to be formed on the vinylic carbon. Now this C double bond C positive charge is called vinylic carbon, and we know that this is sp2 hybridized carbon and a very electronegative one. So that means you will get very unstable carbocation, and hence we require the presence of this Hg2 plus. This stabilizes the carbocation and hence this reaction takes place. Fine. So now we have understood why this Hg2 plus is required and why we get a terminal oxygen, why we get a terminal OH. But there is one more reason why this terminal OH is coming. That is because this can now be converted into this kind of structure. Now if you see that this is forming from this. How? Why? Because this is an enol structure, and you know whenever enol is present, it converts into a keto structure because keto is more dominant or it is more stable. So this is simply keto-enol tautomerism, and from alkyne, the initial product, you get a ketone, and hence this H2SO4 HgSO4 reaction is very important. We have seen through what it undergoes and how it forms the ketone. That is why we have discussed this reaction in detail, because this kind of reaction is not observed in case of alkenes. Fine. Moving on to the last part. The last part is the oxidation of alkynes. Now the oxidation of alkynes with KMnO4 and ozonolysis. With KMnO4, the same products as that of alkenes, the acetic acid is the last. It does not convert into carbon dioxide just because it has got one more pi bond to break. So if you want to write C, and suppose we have this kind of thing. Now here you must observe that we cannot get ketones. We have to get only carboxylic acids. In case of alkenes, we can get carboxylic acids and we can get ketones in case of KMnO4. Suppose you consider a molecule like this. Now this will give you a ketone. When you convert fully oxidized with KMnO4, this part will give you actually a ketone. But this case is not observed in case of alkynes, and we get only and only carboxylic acids. Carboxylic acids or carbon dioxide also. So if you consider this, let's take directly a terminal alkyne. If you write with KMnO4 the reaction for this, KMnO4, then what you get is carbon, carbon, carbon. This carbon becomes the carboxylic acid, and this becomes the carbon dioxide, the terminal carbon. So terminal alkynes will give you carbon dioxide, and all others in which a triple bond is present in the middle of the chain will give you carboxylic acids. So here also there is a slight difference between the reactions of alkenes and alkynes. What about ozonolysis? In case of alkenes, we obtained only aldehydes or ketones. What about alkynes? In case of alkynes, we observe that we get only ketones and carboxylic acids. That is, the aldehydes that are produced are further oxidized to carboxylic acid, and since ketones cannot be oxidized, they remain as ketones. So as the final reaction for this lecture is the ozonolysis of alkynes, that is C triple bond C, CH3, CC, and if you do the ozonolysis for this, what do you get? Reactants you must write Zn and CH3COH, what we get is CCC double bond OH plus CH3 C double bond OH. So what we get is two molecules, one molecule of acetic acid and one molecule of propanoic acid. So this is the result of ozonolysis, quite similar to KMnO4 except for the fact that we have a reducing agent over here. But this reducing agent, the job of this is to reduce, to stop the reaction at this point. Although the reaction cannot go further, that means if you take a terminal alkyne, you do not get a carbon dioxide molecule in case of ozonolysis because of the presence of Zn. The carbon dioxide is not produced and you stop at the stage of formic acid. So this is the final product. So if you ozonolyze this, you will get normally propanoic acid, and with this carbon you will get the formic acid and not carbon dioxide. So this is one of again a difference between ozonolysis of alkenes and ozonolysis of alkynes. We have come to almost the end of the lecture, but except some few points that I would like to add about the elimination reactions, especially the E2 reactions, in which we know that the reaction takes place simultaneously, that is the base abstracts the proton and then the halide will leave giving you the alkene. But I would like to just discuss the rates of different halides, for example fluoride, chloride, bromide and iodide. How much percentage of the major product, that is this elimination product in E2 case, will be absorbed when these undergo the reactions. So let us see fluorides, it is quite less, 35% and 70% for chlorides, 90% and is almost 99%. So okay, I have just given the reverse. This is most of the reaction of fluorine will be through E2. There is 60% of the reaction will be through this, 30% through this, 10% through this, and almost very less percentage. Most of it will undergo through E1 because iodine is very bulky. So that is why E2 is quite difficult, and that is why E1 is most preferred in case of this. So these are the percentages of yields of the product that will be obtained. Now let us see something about the basis, the nature of base, how it affects the elimination reactions. So now base, what is the role of a base in elimination reaction? To abstract the proton either after the formation of the intermediate in case of E1 or in the same transition state in case of E2. So our base needs to be lesser bulkier, because if the base becomes more bulky, it becomes really difficult to abstract the proton, and even if it abstracts the proton, that gives us a lesser substituted product. As we have seen in case of E1, in E2 also same thing will happen. That is, if we have some alkene, suppose bromine over here, if the base is really bulky, if you take suppose potassium butoxide, which is this O minus, and we have K plus like this. So this base is literally very bulky, and if this is abstracting a proton, for example this proton, and if we have a possibility of, let us create such a situation, if we have something, okay, now if we take an alkene which is like this, quite obviously this is a much more stable alkene than this probably, so, or this probably, anything, even this also. So but if I take a bulky base like this one, then this hydrogen would be really difficult to abstract, because it is bulky and already this is a tertiary carbon. So it is surrounded by groups on three sides and by one hydrogen, and if the base has to take that hydrogen and it has to come from the other side of the halogen, then it has to face the repulsion of the 3 alkyl groups. So that is why in these cases the lesser substituted product of preferred will be this one. So that the hydrogen just like that goes from away from this carbon and we get an alkene which is like this. So we can just complete the reaction also. If we take an alkyl halide, let us take any alkyl halide which is something like this, Br hydrogen hydrogen. Now with this carbon, if Br is present and we have these two hydrogens and configuration can be made anti, there is no problem at all. But these two, out of these two, which one will eliminate if we use the base potassium butoxide. That explanation I have given you, that the lesser substituted product will be forming, and which is called the Hofmann product. The more substituted product we have seen, it is called Surjev product. I have told you in case of E1, just an explanation of the same thing in E2. Even in E2, the same rules are followed, that is the base abstracts that proton if the base is bulky, which forms a lesser substituted alkene. So here we have this kind of product, and of course we need to provide some heat over here so that the elimination takes place. But if the base is not bulky, even in E2 case, if there is a hydrogen which is present, which can be present in an anti-configuration to the halide, then in that case we go for the most stable alkene. But generally it is not observed that we have that hydrogen. In the questions, they will never give you, almost never they will give you a hydrogen which leads to a more substituted alkene which can be in anti-configuration to the halide. That is the test they will try to test, whether you go for the most substituted one or the lesser substituted one. Even for the small base, in those cases, most substituted will not form. Don't make that mistake, please. So that is it, and this was it. We can also consider one example if you like. Let us see this one. If we have something here and we have this hydrogen CH3, Br hydrogen, something CH3, and if to make this question more complicated, what I can do is I am getting this alkene, and yes, correct. Let me put a hydrogen here. Let me put a hydrogen over here. So now that is good, and that's it. So now, which if I treat this with a small base, not a bulkier base but a non-bulkier base, for example KOH, ethanol. So now what will be my major product? First of all thing, you must observe that which one is giving you the product, this hydrogen, this hydrogen, this hydrogen, or any other hydrogen. You will observe that the condition in this case, if we go with E2 mechanism, is that it should have an anti-coplanar hydrogen, that Br, and the only other possibility is this hydrogen. So that is why, whether it is a bulky base or not, only this alkene is forming. If suppose there was a possibility here, then probably most substituted alkene would have formed. But here we have taken this example just to explain my previous point. So that is it. Now I would like to add, this is all about elimination reaction which I wanted to add. Let me talk something about ozonolysis here. Ozonolysis we have seen in great detail, but we haven't seen one feature of ozonolysis, that is oxidative ozonolysis. What is this? Oxidative ozonolysis. This oxidative ozonolysis is actually ozonolysis without zinc. If you remember what is ozonolysis, then if we take some alkene R-R First reagent O3 ozone, second reagent we had Zn, but now in this oxidative case we exactly don't have this Zn. If we had Zn and we take suppose acetic acid or something, then we get different ozonolysis products. In this case R, C, double bond O. If this is H, then we get an aldehyde, and if this is H, then again we get R dash C double bond O H. If suppose they are R groups, then we will obviously get the ketone. But suppose these are hydrogens and you remove this zinc, what happens then? If you remove this zinc, then if you look at the mechanism, the formation of ozonide and all that, then you will observe that this hydrogen will not be just hydrogen, this will not be an aldehyde, this will be oxidized to the highest level, and this will be actually carboxylic acid, because the role of zinc is just to prevent the oxidation to carboxylic acid. If the zinc itself is not there, then it will directly oxidize to carboxylic acid. And suppose here we have R groups, then it will remain as ketone. As you know, ketones cannot be oxidized to carboxylic acids. So if we don't have zinc over here, then what we get is the oxidative ozonolysis. A very simple thing, but just in case in exam if it comes that O3 and this reagent is given, then you should not get surprised or you should not panic. You must know that if zinc is not there, what is the role of zinc? Depending on the role of zinc, we can easily write the products. Fine. So this was about ozonolysis, oxidative ozonolysis. Now something about ozonolysis. Ozonolysis, we know that the reagent is this Zn, H2O, acetic acid. Fine. Now this ozonolysis can also be performed by using H2S. Ozone and H2S, that does the same thing. H2S will do the same thing, that it will stop the oxidation from going to the carboxylic acid level. It will just stop at the aldehyde or the ketone level. So this was about oxidative ozonolysis and ozonolysis. That's it, I think. And except for one more thing, that oxidation of alkenes, if we are talking about, then we can also talk about the oxidation with KMnO4. KMnO4 I have discussed only one case, in which case the KMnO4 is dilute and it doesn't get oxidized to the maximum level. But actually KMnO4 in base gives you aldehydes if alkenes are present, if it cannot form ketones. For example, let us take hydrogen CH3, hydrogen CH3. If I treat it with KMnO4, cold, dilute and alkaline KMnO4, then I will get normal products, I will get an aldehyde, I will get an aldehyde. But suppose I add hot acidic KMnO4, then in that case we don't get the aldehydes, it goes to the farthest level, that is the carboxylic acid. If it is a ketone, no problem, we don't have any problem, we will get the ketone. And in neutral medium also, it does not act as a very high oxidizing agent. Only in acidic and the basic medium we get the differences, that in basic medium this KMnO4 will oxidize to a very small extent and will just convert to aldehydes or ketones. But if it is acidic and hot, then we will get ketones or carboxylic acids. To the maximum level it will oxidize, it is a very, very strong oxidizing agent. So this was it about this chapter, some few extra points just to enhance your knowledge. Although I have taught the theory, but sometimes these are also asked in the examination. So I hope you have liked the lecture. Please go through all the mechanisms carefully, because the mechanisms are really important if you want to write the product. It doesn't matter how many questions you solve, if you know the mechanism correct, you will get the answer. So that was it. Thank you.